biology students, he's doing some root mounting, so he's stained some roots, which he's got here. He's stained them in acetic acid and ink solution, which basically makes the fungal hyphae inside the plant roots visible.
Yeah.
And you can see various stages of it happening here. So they're like harvesting them from the soil, picking them out, and they put them in these cassettes into the stain. And then we look at them down a microscope. So you can have a look at some down a microscope.
Yeah, cool, yeah.
Got some really nice ones.
I'm really intrigued to find out what really nice ones means in this context.
Yeah, I mean, this is kind of the stuff that we look for.
Yeah.
So this is the plant root cells in here. So this is the plant root, the vascular bundle here, and then this is kind of the fungus growing inside the root.
Okay, yeah.
And it's through these structures, so these arbuscules here, that they do like the carbon for nutrient exchange.
Right.
And that's kind of how they form those symbioses. So if I turn, this is where I can't work my own stuff. So I've got some nice example ones. What did I do with them? They're in here.
This looks like a very expensive small room.
Yeah, it's nice actually. Some.
I can't imagine these to be particularly cheap.
Yeah, so these aren't too bad. These are like sort of £1,500.
Yeah.
So they're kind of pretty basic ones, really. People spend an awful lot more. I was trying to find something we're going to see something decent in, because these ones aren't really. These are probably good. Let me just have a look at this one. Oh my god, that's dangerous.
We'll delete that bit.
Wow,
Actually.
yeah, please do. I'll leave it in. I don't suppose it's going to be broadcast. Right, this is probably good. So you kind of like mount the root samples like this, and you can kind of just scan through them. If I think good to show you. I've got to pick a really good sample. Oh no, there's stuff in there.
Yeah.
So if you look down here, you'll see it's kind of like a big mess of root, and then you'll see fine blue strands in there, and blobs, and like that's the fungus in there.
Right.
And you'll see some arbuscular structures and some because that's really slidey, by the way. So just be careful on that. Then it will grow out of the root into the soil, and like forage for nutrients and stuff in the soil.
Yeah.
And it kind of basically, by doing that plant root system, is vastly bigger than it would be on its own.
Right.
Because it kind of like, if you can imagine the root systems like that, and then the fungal hyphae go from loads, like many meters further out.
Yeah.
So it gives it like a much greater volume of soil it can explore, which is why it's kind of advantageous, in particularly in poor nutrient areas, to form those symbioses.
Yeah.
So it just gives you more soil to explore. And also the fungi can get nutrient ions out of different sources in the soil than the plant can. So like from rocks, it can dissolve rock and like take it out of there.
Yeah.
Which obviously plant roots can't so much.
Yeah.
So it's a real advantage for them to do that. So that's the type of fungus we're really interested in my group. And we're kind of interested in how, like, what do they do? So these posters kind of illustrate that quite nicely. So we have 3 different strands of work that we're doing. So we have like interactions with biological systems. So we use parasitic nematodes as like an extra interacting factor. So if we have a plant root here, for instance, where it's interacting with mycorrhizal fungi, but it also gets interacting with nematodes. It gives it an extra pressure for plant resources. So where does the carbon go? How does the plant make a decision to give carbon to a helpful symbiont versus like a parasitic one?
Yeah.
Does it make a decision, or is it just like stochastic?
So do some have like a defence against those specifically?
Yeah, exactly. Yeah, they do. And what we're finding is actually that the mycorrhizal fungi actually enhance that defence system against the parasites. And so what it ends up doing is kind of this, where the plant ends up, because the defence has been enhanced by the fungus getting in the root, it is able to decrease the amount of carbon that goes into the parasites compared to the fungus.
Right.
Which is really cool. It's kind of, it's a bit like a vaccination, because when that fungus gets into the plant roots, that triggers like all of that immune response.
Yeah.
But the plant somehow, we don't know how, it knows it's a friendly symbiont rather than like a pest.
Right.
And so at some point in that whole cascade of like getting really arsy about a parasite getting into roots, it stops that happening. It's like, oh, actually, this is fine, continue. And because it's done that, when a pest does try and get in the root, the plant has like this really fast response to it. It's just exactly like we would with a vaccination.
Yeah.
So like it suddenly triggers an immune response much more quickly and much more effectively. So there's kind of like this priming effect of mycorrhizas as well as the nutrient uptake thing, which is really cool. The other thing we're interested in is in agricultural systems, so food production, to try and replace like chemical pesticides through that mechanism, and also fertilizers. And what we find is that different types of crops, different cultivars, they form mycorrhizas to a better or worse extent. So they're either like more helpful or less helpful, depending on the type of the cultivar that it is that you're growing. Miles's PhD is looking at heavy metal interactions. So this is like an urban horticultural context, so like allotments and stuff. And actually a lot of allotments have got loads of heavy metal in the soil. But we don't know how that impacts on soil health and function, particularly mycorrhizal fungi. So he's doing a bunch of experiments looking at how that interaction is affected by things like zinc. Zinc particularly because it gets applied when you add manures, which a lot of gardeners do. That inadvertently introduces zinc into the system. So he's doing that. And then we've also got this one's a really cool project with the antifungals. So this is looking at like regenerative agriculture and circular agricultural systems where farmers apply wastewater, sludges, slurries to the land instead of fertilisers. You got to apply them.
I thought I felt something kind of weird. I thought it was just a
fresh,
wind blowing or something.
So by doing that, the idea is if you're a farmer, you can apply less fertiliser and stuff because you're using like what do they call it? Grey water. You know. Unfortunately, what we don't know about is, or what my collaborators in Leeds discovered is that by doing that, you actually introduce bioactive concentrations of drugs into the soil. So things like pharmaceuticals that don't get removed through the treatment that the wastewater goes through, because it's not designed to do that. Like it's supposed to just get flushed into the sea, right, or whatever. But when it gets into the soil, it gets assimilated into plant tissues. What we absolutely have no idea about is how it interferes with fungus. And in the antifungals in particular, you might imagine it's probably pretty bad for them. And what we found is really cool, because it isn't that it gets rid or kills the fungus at all. The fungus is still there, so it's still be seeing it in the roots, but it's just stopped delivering any nutrient to the plant. And so it switched it from being like a mutualist, where both of them are benefiting from the relationship, it's turned into parasite because it's still taking carbon. So you kind of changed the nature of the relationship, so suddenly instead of being beneficial, now it's become parasitic. Which is pretty cool.
Purely by human intervention.
Pretty exciting. Well, it's got massive, because it should be a really good thing, doing this circular, using wastewater and sludges, slurries and so on, because it's very like recycling all the nutrients in the system. But it's not without its problems, and we don't tend to think about that. We tend to focus on the good news story, and it's a very green sort of circular system, and that's great for the environment, for resource capture, etc. But actually it does have problems that need addressing. So we're kind of quantifying that in different crops now.
Very interesting.
So that's cool. So if we go, I'll show you. We'll go down to the annex and I'll show you.